Our universe is filled with mysteries. Some are out in the vast cosmos, others hide in plain sight, in the everyday things we take for granted. One such enigma is the Mpemba Effect, a phenomenon that challenges our basic understanding of heat and cold. Imagine a race between two containers of water, one hot, the other cold, both placed in a freezer. Logic dictates the cold water should freeze first. Yet surprisingly, sometimes it's the hot water that turns to ice quicker. The story of this counterintuitive phenomenon begins in 1963 in Tanzania with a curious schoolboy named Erasto Mpemba. Erasto was making ice cream in a school cooking class. The recipe required boiling milk, then cooling it before freezing. In a rush to secure a spot in the overcrowded freezer, Erasto put his still-hot milk mixture in alongside his classmates' already cooled mixtures. To his astonishment, Erasto's hot milk froze into ice cream before anyone else's. This wasn't just a fluke. Erasto noticed this strange effect again and again in other experiments with water. He even questioned his science teacher about it. The teacher, bound by conventional wisdom, dismissed Erasto's observations as impossible. However, Erasto remained persistent. He knew what he had seen. Years later, a chance encounter with a visiting physicist gave Erasto the opportunity to share his findings. Together, they conducted rigorous experiments, confirming the phenomenon that would come to be known as the Mpemba Effect. The Mpemba Effect challenges what we think we know about heat transfer. We learn that heat flows from hotter objects to colder ones until they reach a thermal equilibrium. So it seems logical that colder water, being closer to the freezing point, should freeze faster. Yet the Mpemba Effect demonstrates that under certain conditions, hot water can cool and freeze more quickly. This apparent defiance of common sense has sparked much debate and investigation within the scientific community. Despite decades of research, there is no single universally accepted explanation for the Mpemba Effect. Several theories attempt to unravel this intriguing mystery. Some scientists believe the answer might lie in the different properties of hot and cold water molecules. Others point to external factors like convection currents or the presence of dissolved gases. It's likely a combination of factors contribute to this perplexing phenomenon. Section 6. Evaporation's role. One prominent theory centers on the role of evaporation. Evaporation is a fascinating process where liquid water transforms into vapor, a gas, and escapes into the air. This process is influenced by several factors, including temperature, humidity, and air movement. Scientists have long studied evaporation to understand its impact on various natural and artificial systems. When hot water is exposed to air, it evaporates more quickly than cold water. This is because the molecules in hot water have more energy, allowing them to break free from the liquid's surface tension more easily. As these high-energy molecules escape, they carry heat away from the remaining water. This evaporation removes heat from the water, effectively cooling it down. The process is similar to how sweat cools our bodies. When we sweat, the moisture on our skin evaporates, taking heat with it and helping to lower our body temperature. While this might seem counterintuitive, remember that evaporation is a cooling process. It's a fundamental principle of thermodynamics. The energy required for the phase change from liquid to gas is absorbed from the surrounding environment, which in turn cools the remaining liquid. It's how sweating helps regulate our body temperature. Our bodies produce sweat to cool down when we overheat, such as during exercise or in hot weather. The sweat evaporates, removing excess heat and keeping us from overheating. So, even though you start with a hotter sample, the faster rate of evaporation could give it a head start in the race to freezing. This phenomenon is known as the Mpemba Effect, where under certain conditions, hot water can freeze faster than cold water. Scientists are still exploring the exact mechanisms behind this counterintuitive observation, but evaporation plays a crucial role. Section 7. Dissolved gases and convection currents. Another theory focuses on the behavior of dissolved gases in water. Dissolved gases, such as oxygen and carbon dioxide, are present in varying amounts depending on the temperature of the water. When water is heated, these gases tend to escape more readily, reducing their concentration. This phenomenon is crucial in understanding how water behaves under different thermal conditions. Hot water tends to hold less dissolved gas than cold water. This is because the increased kinetic energy in hot water allows gas molecules to escape more easily. As a result, hot water has a lower concentration of dissolved gases compared to cold water, which retains these gases more effectively due to its lower kinetic energy. These dissolved gases can act as insulators, slowing down the freezing process. When water contains a higher concentration of dissolved gases, these gases can form a barrier that hinders the formation of ice crystals. This insulating effect can delay the freezing of water, making it an important factor in the study of thermodynamics and phase transitions. Therefore, the lower concentration of dissolved gases in hot water might facilitate faster cooling and freezing. This counterintuitive observation, known as the Mpemba Effect, suggests that under certain conditions, hot water can freeze faster than cold water. Scientists are still exploring the exact mechanisms behind this phenomenon, but the role of dissolved gases is a significant area of interest. Additionally, convection currents within the water could play a role. Convection currents are the circular movements of fluid caused by the variation in temperature and density within the fluid. In water, these currents can significantly influence the distribution of heat and the rate at which the water cools or freezes. Hot water, being less dense, circulates more rapidly than cold water. This rapid circulation helps to distribute heat more evenly throughout the water, enhancing the overall cooling process. The movement of water molecules in hot water is more vigorous, leading to a more efficient transfer of heat to the surrounding environment. This faster circulation could enhance heat transfer, leading to quicker cooling. By understanding the interplay between dissolved gases and convection currents, scientists can better predict and manipulate the thermal behavior of water in various applications, from industrial processes to natural phenomena. Section 8. The importance of impurities. Furthermore, the presence of impurities in the water, such as minerals or dissolved salts, can significantly influence the freezing point. These impurities can disrupt the formation of ice crystals, requiring lower temperatures for freezing to occur. The specific composition of impurities could differ between hot and cold water samples, potentially contributing to the observed differences in freezing rates. Section 9. A continuing enigma. The Mpemba Effect, though discovered decades ago, remains a fascinating puzzle for scientists. Named after Erasto Mpemba, a Tanzanian student who first observed the phenomenon in the 1960s, it describes the counterintuitive occurrence where hot water freezes faster than cold water under certain conditions. This paradox has intrigued and baffled researchers for years, leading to numerous studies and experiments aimed at uncovering the underlying mechanisms. It highlights the complexities of seemingly simple phenomena and reminds us that our understanding of the natural world is constantly evolving. The Mpemba Effect challenges our preconceived notions and encourages us to look deeper into the principles of thermodynamics and molecular behavior. Each new discovery adds a piece to the puzzle, yet the complete picture remains elusive, driving scientists to continue their quest for answers. Studying this effect could lead to advancements in various fields, from improving our understanding of climate change. The insights gained from investigating the Mpemba Effect could help us better predict and model the behavior of natural systems, particularly in the context of global warming and its impact on ice and water cycles. This knowledge is crucial for developing strategies to mitigate the effects of climate change and protect vulnerable ecosystems, to developing more efficient cooling technologies. By exploring the principles behind the Mpemba Effect, engineers and scientists can innovate new methods for refrigeration and thermal management. These advancements could lead to more energy-efficient cooling systems, reducing our carbon footprint and contributing to sustainable development. The potential applications are vast, ranging from everyday household appliances to industrial processes and even space exploration. The quest to unravel the secrets of the Mpemba Effect exemplifies the spirit of scientific inquiry, the relentless pursuit of knowledge, driven by curiosity and a thirst for understanding the universe and its many wonders. It serves as a reminder that science is not just about finding answers, but also about asking the right questions and embracing the unknown. As we continue to explore this enigmatic phenomenon, we are reminded of the boundless potential of human ingenuity and the endless possibilities that lie ahead in our journey of discovery.